What's going on, data devotees? It's Jameson here. This video is on logical vectors. What are they? What do they do? How do you use them? Well, it turns out that even though they're just comprised of essentially values of true or false, they can be extremely useful when it comes to creating certain conditions for your data, which are true whether those conditions are met, and false when those conditions aren't met. And this allows you to create advanced sort of filtering statements that allow you to create subsets or smaller sets of your data, whether or not they pass a given set of criteria or a criterion that you've set forth and you want to use to be able to sort of say, hey, you're invited to the data party and you are not invited to the data party. Without further ado, let's jump right in. So I've got RStudio opened up here with a relatively clean slate, and I'm going to go ahead and simply press Control-Shift and N to open up a new script, and then we'll go ahead and save our script as simply my script. And of course we're using the extension .r because we want to always use the proper extension for our R scripts. Alright, so what is a logical vector or a logical value? Well, again, logical values are comprised of trues and falses. So if, for example, you have a true, in fact, we'll just have that alone. We'll save that as t. And if you have a false value, we can save that as f. We have true and we have false. And now these are highlighted blue because R actually recognizes these as logical values, which is different from recognizing them as an object. For example, if we were to simply try and run false with lowercase, it says object is not found, but if we did false with uppercase, then it prints out that false is in fact equal to false. Cool. So we can create vectors of true and false values, and again, these are called logical vectors. So by using function C, or combine, we can combine multiple logical values together. So let's give that a try now. So here's true, false, false, true, and true. And if I run that, it's simply going to reprint those true and false logical values. NA is also included, in other words, missing values, and that is something to be aware of as well, but we'll get to that a little bit later, and you shouldn't really have an issue with that too much. So let's go ahead and save this as logvac for logical vector. And so now we've saved that object up here. Logvac contains 5 elements: true, false, false, true, and true. How do you know that it's logical? Well, you can use, for example, function class. And if I do logvac and pass that as an argument into function class, we get logical. So what else? So logical under the hood is actually binary, and that makes this extremely important for when it comes to using these with mathematical or arithmetic operations. And so if we wanted to, we can actually use function sum, and we'll pass that to logvac. And if we do that, it's going to give us 3. Now, why is that? Again, it's true, false, false, true, true. And that's because under the hood, if we use function as numeric, a true, which by the way, you can abbreviate as a T, but I do like to write it out, a true is equal to 1, whereas a false is equal to 0. And so that means that when you pass function sum, which sums up a series of numbers, you're essentially just counting the number of trues since they all equal 1. There are 3 trues in logvac, and so therefore the sum is 1 plus 0 plus 0 plus 1 plus 1. And let's go ahead and turn that whole thing into numeric just to further demonstrate that. So again, it is 1, 0, 0, 1, 1. And that's under the hood, but what we see and what R tells us is true, false, false, true, true. You can also use functions like mean. And mean just provides the average. When you provide the average of ones and zeros, you're actually providing the proportion, in this case 60% of all the values that equal true. So since there are 5 values here, and 3 of them equals true, that's 3 out of 5, and 3 out of 5, we can multiply that by 2, for simplicity, becomes 6 out of 10, and therefore that's 60% of all your values are true. This can actually become very, very useful, very important when it comes to programming, when it comes to, especially for analysis, and we'll talk about why right now. But first, let's get into how we typically create logical values. Now, logical values are, again, the result of whether or not a condition is met. So if your condition is, does this vehicle have a miles per gallon over 20 or 20 miles per gallon? If it's true, then it gets returned true. If it's false, it gets returned false. So let's demonstrate that. We'll use the dataset Iris, and Iris again contains 150 different observations of 3 different species of iris. And so what we can look for is, let's see, petal length that is greater than 1.2. So if we extract the variable petal length, in effect, this creates a vector. This is no longer tabular data. It is a series that we can display horizontally now of these 150 values that exist within variable petal length. And so when we extract it, we can now subject it to what's called a relational operator. So this is, of course, greater than, and we said greater than 1.2. And now, because we've turned these values into instead a conditional statement, we are subjecting each individual value or each element in this vector, we are subjecting it to this test. Is it greater than 1.2? And so here we see true, 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 false, 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 etc., etc. So we kind of see this mix. Let's see if we can do greater than 1.5. That's a little bit more stringent. Now we have different species with longer petals than others, and so it seems like the initial 50 observations do have shorter petals, and that's why we're seeing falses occur kind of in the beginning of that. But there are other relational operators as well. So let me just mark that here. Again, that's a relational operator. And so if we wanted to, here, let's run through the entire gamut. We've got greater than, we have less than, we have greater than or equal to, we have less than or equal to, we've got exactly equal to, and we've got not equal to. So that exclamation mark is really what's called negation. And so you can use this for other values as well. And in fact, if we took this entire statement, which is again comprised of all of these trues and falses, we can put in front of that this negation, and we can make that the opposite. So now we have a bunch of trues in the beginning, and then the rest are false. Notice how that's different from without negation. We have a bunch of falses in the beginning, and then we have trues. So yeah, these are your logical operators, and this is how you create a conditional statement. So let's look for a different way that we can do this. If we did iris petal length, and we wanted to find those that are exactly equal to 1.2, it looks like we've got we've got a couple trues in there. And again, we can find out how many are true by using sum, because true equals 1 and false equals 0. So here it returns 2. Let's see that again with a cleaner console. So again, sum is used, and we find that 2 out of these 150 different observations, 2 of them are actually true. And we can find the proportion of that with mean. So 1.3 repeating percent of all of these observations has a petal length exactly equal to 2. But we can try something else as well. Let's go ahead and do a different variable. In this case, we'll do species, and we'll do exactly equal to, and it's going to be in characters. It's going to be a character value, so we want to put it in quotations, and we'll use setosa. So, of course, setosa is ultimately the first 50. Remember, these numbers here indicate what position this element is in this vector. So this is the 33rd value. This is the 49th value. And at the 50th value, we can see that true stops. That's because the first 50 values are from the species setosa. Now, if we change that to versicolor, we can see that the middle 50 observations are actually from the species versicolor. And again, we've got setosa, versicolor, and virginica all having 50 observations each. And this is Edgar Anderson's IRIS dataset. So this is, again, making this multiple different ways to create conditional statements, and you're asking R to evaluate whether or not that condition that you create exactly equal to versicolor, exactly equal to 1.2, greater than 1.5. If the value in that variable passes that little test that you've created, in effect, it becomes true. If it doesn't pass, it becomes false, and that's how logicals are made. Right on. So what if we want to do more than one conditional statement? And so in this case, we can use what are called logical operators. And logical operators are, essentially there are two. We have and we have or. And so the difference is, well, first of all, let's see it in action. So if we had petal length greater than 1, let's see how many trues. I guess they're all true on that one. Let's do petal length greater than 1.4. So we got a little bit of a mix. And excuse me. And we also want another condition to add on to this. We want to use petal width is less than, well, I'm not really familiar with the petal width values. We'll do less than 0.8. Okay, so we had a few of these that actually passed that test. The first three observations, or first three values, did not pass this test. So in other words, they were neither greater than 1.4 or they were not less than 0.8. And that's because with the AND logical operator, the left condition has to be true and the right condition also has to be true in order for this entire expression to be true or treated as true in its entirety. What about OR? Well, if we did this instead, and let's actually get the sum of these. Let's see how many of these are both true on the left condition, what's called the left operand, but you don't need to know that, and the right operand, or the right condition. So 26 of these observations have both true in terms of this condition and true in terms of that condition. And that's because our AND logical operator states that we need both of these conditions to be true in order for the entire expression to be true. But what about OR? If we do that, well, that's interesting. All of this is true, and that's pretty amazing because it seems like petal width probably is, and I think these are in centimeters maybe, or inches. I can look that up in the documentation, or you can. That's up to you. And so all of these become true. And why? Because or only one condition needs to be true. We already know that this petal length is greater than 1.4 has a list of trues and falses, but petal width has ultimately a bunch of trues, and it's either this or this needs to be true. They all end up being true. We can determine that, of course, with sum, and it's 150. Let's try this out with one more example using empty cars, right? A little bit less abstract than looking at irises. So in empty cars, we have cylinders, and we can do cylinders exactly equal to 6. So of the 32 vehicles in empty cars, which you can see here, we have a series that are true. Yes, they are exactly equal to 6-cylinder engines, and falses, no, they are not exactly equal to 6-cylinder engines. In fact, we can reverse that with are not equal to 6-cylinder engines, and then we can pull up whether that's true or false. Now, if we do and, so let's go back to exactly equal to. So we're looking for 6-cylinder engines, and then we want empty cars, automatic or manual, and we want, I believe one is automatic. No. Yes. Well, at any rate, so here we can find which empty cars is has a cylinders equal to 6, and then we can also find which of them have an automatic or manual transmission exactly equal to 1. And so in this case, both of these have to be true. Both of these conditions are met. Now, what about if we do an OR? Let's actually find out how many cars in the empty cars data set meet these criteria. 3. So if we make this an OR, it's going to be less stringent because we're saying it's true if the car has 6 cylinders, and it's also true if automatic or manual is exactly equal to 1. So we are probably going to have more cars pass this because it's less stringent in terms of being a condition that filters out yeses and nos or trues or falses. And so, of course, yes, we get a much larger number. A little bit more than half of all cars in this data set are either an automatic or manual of equal to 1 or a cylinder exactly equal to 6. And so that's a bit, as you can see, that's very helpful when it comes to combining these different conditional statements using either an and or an or. Again, these are called logical operators. Okay, so what about selector vectors? In other words, using trues and falses to be able to select which values and which rows those values are located that we want to preserve, or that we want to kind of differentiate from the rest of the data because they pass some sort of a condition, right? And so we call those selector vectors because we create these vectors of trues and falses, or these logical vectors, and that allows us to be able to pick out just the observations that meet a certain criteria. So if we say empty cars, and we'll say miles per gallon is greater than or equal to 22. So this becomes our selector vector. But first, in order to understand how to use selector vectors, we have to understand something called subsetting. So in subsetting, you take the name of the data set or the object which contains your data, and you're able to use brackets immediately following it. Now pay close attention here because I used to struggle with this a lot when I was first learning R, and that's okay. It takes a minute to be able to get used to this. So because we have tabular data, we have 2 position locations. Let's go ahead and take a look at empty cars to really understand this a little bit better. So in your first location, that's on the left side of this comma in brackets, these are your rows. And you can indicate, for example, that you want the first row. And if you don't indicate anything to the right of the column, to the right of the comma, that means that you want all of the columns. So this indicates the column position. Again, so rows to the left of the comma and columns to the right. So what happens when we run this? It returns the first row because we've indicated that we want row number 1 and we've indicated nothing in columns, so it's going to return all of the columns. But what if we want rows 1 through 5? Now that returns the first 5 observations, and of course all the columns because we didn't specify anything in the column position. Now what if we want rows 1 through 5 and we also want variables 2 through 6? So let's go ahead and do that, 2 through 6. And of course this is creating a subset or a smaller data set from our original data set. And it's because we've specifically said, explicitly specified that we want these first 5 columns, rows, and we want these columns 2 through 6. So we get cylinder through weight. Now if you want to mix and match, you can put these into the combine function. And so we can say 2 through 6, and we'll take column 10. There are 11 columns total. So that includes gear. Not too bad. And if we want 1 through 5, we can say 1 through 5 in function C, and then we can also add that we want 10 and 15. So we want the 10th and 15th rows as well. Let's clean that up a bit. Cool. So because we mentioned 5 rows, 6 rows, 7 rows, we get 7 rows or 7 different vehicles returned to us, and then also we mentioned that we want 4 plus 1, 5 columns, and we specify what those are. Now another cool thing that you can do is you can actually specify columns by name, and if your rows have names, you can also specify by row names. So in this case, we're just pulling out the MPG for these 7 vehicles. If you wanted to, if your data do have row names, you can also specify by row name. And that's just another way to be able to subset data. So the MPG, or miles per gallon, for the Mazda RX-4 is 21. And again, those are the first row and the first column, and we're just indicating, we are just indicating that we want to pull the value for that column and that row. And sure enough, it is in fact 21, as you can see here. So that's subsetting in a nutshell. There are a few different things that you can do with that to mess around. But what happens with selector vectors? Well, if we were to say that in the row position, we only want to select trues and we want to not select falses, well, let's go ahead and I'm going to name empty cars MPG greater than or equal to 22, which is a series of trues and falses. I'm going to send that to object index. So now index contains that series of trues and falses. Anything that is true when you put it into the row position when you're indexing will be returned, and anything that is false will not be returned. Hence, these are called selector vectors. And so here we have only the observations or only the vehicles and empty cars which pass this condition, right? But we don't have to stop there. In fact, we don't have to add that extra step, although I do like naming things as object index. It does make for cleaner code, but in fact, we can put the entire logical expression in the column position and we can return the exact same thing. We can also change it up for example, cylinders are exactly equal to 8. Let's look at the heavy vehicles here, the real sports cars. I mean, it is a kind of a Motorhead, Motor Trend magazine. So, yeah, so these are all the 8-cylinder engines, and that's because we've put this condition in here, empty cars variable cylinder needs to be exactly equal to 8. We've put that to the left of the comma, which is the row condition. And any time that this condition is true, it will return only those observations where it is true. So again, this is called subsetting, and this is the reason why a series of trues and falses is called a selector vector. You are using it to select only the rows that pass a certain condition. We can also use a logical operator to create another condition if we wanted to. So we can do cylinders equal 8 and let's see, automatic or manual equals 1. And so that is a much more stringent filter. It has to both be an 8-cylinder engine and have automatic or manual equal 1. And in this case, we only have 2 vehicles that have been returned to us. So we can see how that's rather helpful when it comes to subsetting or getting a smaller data set based on the conditions that you set, right? So lastly, let's take a look at a couple nuances to trues and false. One thing is that trues and trues are always going to equal true, falses and falses are going to equal false. But when you introduce NAs or missing values, that becomes T and NA equals NA. In other words, this is missing, so that's weird. But what about false and NA? Well, that becomes false. So true and missing is missing, and false and missing is false. So one thing to keep in mind, a little bit of a nuance there when it comes to working with these logical values, these trues and falses, when it comes to having missing data. So again, we're looking at nuances. Now, another thing that you can do with selector vectors are advanced find and replaces. So let's say in empty cars, if I wanted to say, actually, let's go back to, let's stick with that empty cars. Okay, so if I look at empty cars, we have these data, untouched, unscathed, and in fact, let's go ahead and save this as a new data set called cars. So cool. And so cars AM equals 1. What's going to happen if I do this? Well, it doesn't have the comma, right? If we use the comma, we get all of the AM equals 1. Or let's make this a little bit more grounded. Cylinder equals 4. So we get all the 4-cylinder engines when we have the comma, but if we don't have that comma, then we have sort of an issue here, right? It pops up that undefined columns are selected. Well, that's because we got rid of the comma and we don't have anything in the column position, which would normally go on the right side in these subsetting brackets. However, if we were to find, for example, 4-cylinder engines, if we run this on its own, it's going to give us that error. But one thing that you can do here is actually replace any vehicles with 4-cylinder engines with something new. This is going to probably mess up the data set, but that's okay. Oh, actually, so scratch that. Let's use something that doesn't have numeric data, because this, find and replace is going to be easier with, well, if we did, for example, empty cars, cars is exactly equal to 4. There we go. Apologies for that. So what we've done is anytime that there is a 4 that appears in this data set, we have effectively replaced that. So where I messed up was I included a extraction operator and then I included a variable. And so that was a mistake on my part. I do apologize for that. Here, you're in the brackets, you're only using the name of the data set once again, and we're using exactly equals to or not equals to. And we can even change this to not 4. I wonder if this is going to work. This might totally break the data set, but let's find out. Hence why we saved it. Yeah, so really our data are just 4s and not 4s at this point. So we did an advanced find and replace, and anything that was equal to 4, we called it 4, anything not equal to 4. So again, name the data set, and then in brackets, you pass a logical or a condition statement, and you're not specifying any particular variable, you're just specifying the data set once again in brackets. All right, so one last thing that I do want to cover is that let's go ahead and unbreak cars once again. So empty cars is back to normal. And sometimes we have to subset data. So you might have a question like, what proportion or what percent, difficult to type when I have a big microphone in my face, what percent of 4-cylinder engines have MPG greater than 22? Right. So in this particular situation, we need to ignore all 6-cylinder and 8-cylinder engines. We only need to focus on 4-cylinder engines, and then we want to find out the proportion that MPG is greater than 22. So in this case, we actually want to subset and then subset again. So in cars, I'll pass my first logical statement, and that's going to be something that allows us to find only 4-cylinder engines. So we'll do cylinder is exactly equal to 4. That's what that data set looks like once we subset it with a selector vector, or a series of trues and falses, logical values. And so we can subset cars for sil, and I'll name that as a new object. So we're subsetting, and now we want to do another logical operation with this subset of the data, or the smaller set of the data, where we're only dealing with 4-cylinder engines, and we want to find out which of them have an MPG greater than 22. So again, we name the data set. It's getting a little bit long here. MPG greater than 22. And so it turns out that 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, as opposed to 11, 9 out of 11 indeed have an MPG that's greater than 22. And this allows us, in effect, to be able to take the average of, for example, MPG. Let's see if this works out here. Actually, we could take the, we can find n row as one option, which is 9, and we could divide by n row of just the entire data set. If we do that, it's going to give us 9 out of 11, which is 81%. Another way that you could do this is we can take cars 4-cylinder, and then we can extract the variable MPG, and we can, instead of using this row positions, we can eliminate the comma so that it's simply the vector, and then we're only going to find where this is true, and we're going to extract that. Right. And so this becomes that series of trues and falses. But the simplest way to do this would just be taking this subset and using function mean. And there it is again. We're finding the proportion of trues because we're in effect creating a conditional statement which is true if it is greater than 22 MPG and it's false if it's not greater than 22 MPG. We can use sum to find out the number of trues, and again, to find the proportion, we can use mean. All right, so that is about it when it comes to working with logical operators. This was really a kind of a broad overview on the introduction of logical operators, but it's really important when it comes to creating these selector vectors, creating these conditions for your data so that you can say, hey, I want to include this if it passes some certain criterion that I've set up, and I want to exclude it if it doesn't pass that or other criteria. And so it's extremely important when it comes to filtering. It's extremely important when it comes to kind of basic data analysis, when you're looking at counts, when you're looking at really summary, statistics, and things like that. And you'll be using that a lot in the future to be able to find out which data really do achieve those conditions that you set up. So that all being said, enjoy diving into logical values and filtering and subsetting your data based on selector vectors and your criteria.